Okay, so picking it up now with linear equations with fractions, rational equations. Rational means fraction. So what happens with these is, leave yourself a couple of lines here and we're going to fill that in. I want to take first a look at an example so this will make a little bit more sense. Let's say that we've got the equation x divided by 6 plus x divided by 8 equals 1. Now you know that what's happening here is we've got two fractions that are being added. And recall that when you add fractions, what is it that you have to do in order to add fractions? Yeah, that's right. You got to get a least common denominator. So what's the least common denominator for a 6 and an 8? Yeah, that's going to be a 24. So if I convert this into a fraction over 24 and this to a fraction over 24, then I can actually add those two fractions together because they'll have common denominators. But that means I also need to convert this to a fraction over 24. Well, that's easy because 1 is simply a 24 over 24. That's not too bad. But over here, whenever I need to convert from a 6 to a 24, that means I need to multiply this by 4. And whatever I do on the denominator, I have to do on the numerator because I do not want to change the value of this fraction, only the looks. And essentially, I've multiplied by 4 over 4 is just a 1. And that does not change the value of the fraction. So then this becomes a 4x over 24. Same thing's going to happen over here. To convert the 8 to a 24, I need to multiply it by 3. And that means I need to multiply the numerator by 3. Once again, so I don't change the value of this fraction, only the looks of it. 3 over 3 is essentially a 1, so I haven't changed the value. So this becomes a 3x over 24. Well, the beauty is, now that I've got those common denominators, I can actually add up those numerators and keep the denominators. So a 4x plus a 3x will give me a 7x. Keep that denominator of 24. Well, the interesting thing is, now I have these two fractions that I'm saying they are equal to each other, and the denominators are the same. So if these two fractions are the same and the denominators are the same, well then that must mean that the numerators have to be the same. So that must mean that this 7x has to be this 24. Well, if that's the case, if 7x is 24, then that means I should be able to divide by the 7, and that'll tell me what x is. It's going to be 24 over 7. And once again, some of the books will have you put that answer in set notation, just reminding yourself that you are generating a set of numbers. The only number in the set is 24 over 7. Now I could check it, once again to check. Then that means I take my 24 over 7, put it up here, divide it by 6. I take my 24 over 7 over here, divide it by 8. And I should get a 1 out of that. Well, 24 over 7 divided by 6 will be 24 over 42. And 24 over 7 over 8 will be 24 over 56. And then this reduces to 4/7. And this reduces to 3/7. And sure enough, 4/7 plus 3/7, yep. That gives me a 7/7. And 7/7, sure enough, it really is a 1. So I know that that answer truly is right. But now there's a little shortcut because I know how much you love your fractions, just love those fractions. So I'm going to show you a way to get rid of them. Completely get rid of the fractions. Let's take that same example and do a little something different with it. Let's take it and this time, what if we took that LCD that we had come up with, that 24, and instead of creating common denominators, let's see what would happen if we took the entire equation and multiplied the whole thing by that LCD of 24. In other words, I'm going to take every single term, that's why I put parentheses around the whole equation to remind myself I'm taking every single term of the equation and multiplying it by 24. Now here, When I take this 24 and I multiply it by x over 6, these on these diagonals, they're going to cancel. 6 will go into 6 one time. 6 will go into 24 4 times, and I'm left with a 4x. 8 will go into 8 one time. 8 will go into 24 3 times, and I'm left with a 3x. And then a 1 times a 24 will give me just a 24. So what I have now is a 4x plus a 3x. Well, that's just 7x. 7x equals 24. Well, that's the very same thing that in that first example I had gotten right here. 7x equals 24. So that's a little shortcut that you can take to get rid of your fractions. And the shortcut is you can take the entire equation and you can multiply everything, meaning every single term, by that LCD. And see, I got the very same answer in either case. So when I told you leave yourself a couple spaces here in your notes, basically what you're going to write in here is that to get rid of the fractions, because again, I know how much you love your fractions, to get rid of them, what you do is you multiply every single term by the LCD. Every single term by that least common denominator. And like I said, that gets rid of your fractions. Okay, now sometimes our denominators can be these are simple denominators because all they have in them is a number. There are no variables in the denominators, but sometimes things can get a little bit harder because we can have variables in the denominators, and that complicates things a little bit. But we use the same processes that we did before, and it allows us once again to get rid of those denominators, to get rid of the fractions. So let's take a look at what that looks like. Like I said, the ones before were pretty easy because there were no variables in the denominators. But we're going to throw some variables in and see what kind of difference that makes. Again, leave yourself a little bit of space there. So let's say that I have a 2 over 3z minus a 1/5, and that equals a 16 over 15z. Now it looks a lot like the other one, but it's a little more complicated because of these z's that are down here. But remember, before we said that if we multiplied everything by the LCD, that would get rid of the denominator, and that would make a very simple equation that we know how to solve. So what would be the LCD for a 3z, a 5, and a 15z? Well, if I just look at the coefficients, 3, 5, and 15, well, the LCD for that's a 15. So I'm going to take the whole thing, and I'm going to multiply it by 15, but I'll still have that z in the denominator. Now, if I would multiply everything by that z, then let's see what would happen. So in other words, I'm going to take this first term, I'm going to multiply it by a 15z. I'm going to take this second term, I'm going to multiply it by a 15z, and I'm going to take the back term, the other side of the equal sign, and multiply it by a 15z as well. Multiply every single term by the LCD. Well, back here, this is pretty easy. What happens with the 15z's? Yeah, they cancel out completely, and I'm left with just a 16. Now, the tricky part is in these, but notice here, these z's are going to cancel out completely, and then that 3 goes into the 15. Well, 3 goes into 3 once, and it goes into 15 5 times, and I'm just left with a 10. Here, 5 goes into 5 once, 5 goes into 15 3 times. Now that z is still there, but remember that z is on a numerator now. We've canceled out. We have no denominators anymore because here's a 1. This is understood to be a 1. So we have a 1 in the denominator. My numerator just becomes a 3z. This is very easy to solve because this one, to get the variable all by itself, all I have to do is subtract a 10, subtract a 10. I'm left with a negative 3z equals a 6. And then all I have to do is divide both sides by that -3. And so my z is now going to be a -2. And if I did need to go check that, all I would have to do is put that -2 right where I see the z. And now 3 times -2 is a -6. 15 times a -2 is going to be a -30. And then this becomes a -10 over -30. Sorry, a +10 over -30. This becomes a -6 over -30. So they all have that common denominator of -30. But then subtracting a negative is really adding a positive. So now we have all these common denominators and we work the numerators. 10 plus a +6, sure enough, gives me the 16 over 30. So the left side does in fact equal the right side. I know that this is the right answer. So in other words, when you have variables in the denominator, it really doesn't change a whole lot. Basically, you're going to go back and do the same thing that you had done before, which means that you are still going to multiply every single term by that LCD. Key thing once again is that you have to multiply every single term by that LCD. Now we've got one issue with our rational equations. If you recall back when we looked at rational expressions and we said that there were restrictions on our domains. We said there's certain numbers that cannot go in our variables because they'll create zeros in the denominators. That becomes an issue when you solve your equations, because what if this answer that you come up with is actually the number that would create a zero in the denominator? What if this is the restriction in the domain? If that's the case, then you have what we call an extraneous root. And an extraneous root means, yeah, it's a root, it's an answer, but it's one that won't work. This is again called an extraneous root. But an extraneous root only occurs when the answer that you get cannot be used because it cannot go in the domain. So if we go back and we look at what we originally started with, and we say, well, what's the restriction on the domain? What would cause zeros in those denominators? Well, in all these denominators, the only thing that's going to create a zero in the denominator is if that z itself was a zero. So z cannot be 0. That's the restriction on the domain. But you can see that what the answer that we got is not a 0. It's a -2. So this answer, in fact, really is a good root. It's not an extraneous root. It's an answer that definitely will work. Okay, let's try a couple more examples of these because those can get a little bit complicated. So we're going to practice with those quite a bit. And let's take another one that looks like this. Oops, that should be an X there. Okay, so once again, the idea is I need to get rid of all those denominators. So if I just multiply everything by the LCD, that'll clear out all the denominators. So let's take the whole thing. First off, I got to get rid of the X, so I'm going to multiply by an X. And then I need to figure out what's the number that would clear out a 3 and a 5. The LCD for that's going to be a 15, because that is the smallest number that 3 and 5 will go into. So I'm going to take this side, the 2x minus 2 over 3x, and I'm going to multiply it by 15x, and I'm going to take this side, which is 4x minus 6 over 5x, and I'm going to multiply it by 15x. Now on the left side, when I multiply those two together, what happens is the x's completely cancel each other out, and 3 goes into 3 once, and into 15 5 times. So I end up with 5 times 2x minus 2. And on this side, once again, the x's completely cancel out. 5 goes into 5 once and into 15 3 times, so I'm left with 4x minus 6 times 3. That is a very simple equation that we know how to solve. It's pretty easy to deal with. I'm just going to simply distribute my 5 through, giving me 10x minus 10. I'm going to distribute my 3 through, giving me 12x minus 18. Now I'm going to subtract my 10x to try to get all my x's on one side. That leaves me with a negative 10, and on this side a 2x minus 18. Now the x is over here, so I need to move the negative 18 to the other side. To do the opposite, I'm going to add an 18. Negative 10 plus 18 is 8. Now I get to divide by 2. That tells me that x is going to be 4. But once again, I just need to check and make sure. Now, is this an extraneous root? Because if it is, then it won't work. So if I go back and I look at both of these denominators that I started with, what would create a 0 here? Well, if x was 0, then that would cause a 0 in that denominator. And this denominator, once again, if x was 0, that would cause a 0 in the denominator. It doesn't matter what's in the numerators. It makes no difference at all. You can have a 0 in the numerator. You just cannot have a 0 in the denominator. So x can't be 0, but we figured out the solution is not 0. X needs to be 4. So we know that that solution actually will work, and that's a perfectly legal solution. All right, just a couple more. All right, now that looks kind of complicated because before we didn't have all these extra operations in these denominators. It was just a simple multiplication. But the idea is still get rid of those denominators. What would you have to multiply to get rid of the denominators? Well, both of them have an x minus 2. So if I took the whole thing and multiplied it by an x minus 2, maybe that would get rid of the denominators. So I'm going to take every single term, multiply it by an x minus 2. Every single term. Because when I do that, when I go and I look at this one, these x minus 2's will completely cancel out and I'm just left with a 2. When I look at this one, the x minus 2's will completely cancel out and I'm just left with an x. Here, I need to distribute the negative 2 through, giving me a minus 2x plus a 4. Now that also is a very simple equation that is very easy for me to solve. So I just combine up my like terms here and here. X minus 2x is a negative x. Here's the variable I want by itself. That's pretty easy to deal with as well. I'm just going to subtract the 4. 2 minus 4 is a negative 2. And now I just need to divide by negative 1 to get that x by itself, telling me that x is going to be 2. But now remember, I need to check and see, is this an extraneous root? Well, when I go back up and I look at these denominators here, both of them are the same, so whatever I'm going to restrict in the domain is going to apply for both cases. But what would create a 0 here would be if x was a 2, 2 minus 2 is 0, that's going to cause problems. So that's the restriction on the domain. X cannot be 2, but here it says x is 2. So that can't happen. If I was to go and check this, and I put this 2 up there where I see an x, then what happens is 2 minus 2 is 0. I have an undefined fraction there. Same thing's going to happen here. I have an undefined fraction. So this cannot happen. So this extraneous root is not truly a solution. It can't happen. When that's the case and the root that you got can't happen, then that means there is nothing that will work. There is no number that I could put up here for the x and the x up here and get the left side to equal the right side. There's nothing. When there's nothing, that means there's no solution, and the way that we write no solution is this, the no smoking symbol, or the null set. The null set tells you it is the set that has nothing in it. Sometimes we'll write null set this way, because remember, we're generating a set of numbers. This is the set that has nothing in it. So you can either write your answer this way, or the null set symbol means the very same thing. But that's what happens when the root that you get is actually one of those extraneous roots that I was talking about. Okay, one more. Let's say we've got 3 over x plus 4 minus 7 equals negative 4 over x plus 4. Once again, the whole idea is, all right, we've got fractions. We don't like these fractions. We want to get rid of them. So we're going to take the whole thing and multiply by the LCD. The beauty is this LCD is pretty easy because we have the same denominators in either case. So we're going to take the whole equation and multiply it by this x plus 4. That means take the first term and multiply it by an x plus 4. Take the second term, multiply it by an x plus 4. And take the back and multiply it also by an x plus 4. So what's going to happen here is, remember, these are going to cancel out completely and I'm left with a 3. These are going to cancel out completely and I'm left with a negative 4. And here I'm just simply going to distribute it through. So that'll give me a negative 7x minus a 28. And again, the beauty is this is pretty easy to solve because I don't have any fractions anymore. So all I have to do to solve that one is combine up these like terms. 3 minus 28 is a negative 25. And now to get that x by itself, I simply add the 25 to both sides, giving me a negative 7x. Remember, the sign in front's the sign that goes. That is a negative 7x. And negative 4 plus 25 is going to be a 21. Divide by that negative 7, and that tells me that x is a negative 3. But I need to make sure now, is that going to be an extraneous root? Because if it is, then it can't work. So I go back and I look at my originals. Here's the two denominators. And what's going to happen in them is that to create a 0, x would have to be a negative 4. So I don't want x to be a negative 4. And sure enough, x wasn't a negative 4 in my solution. So now I'm just going to double check and find out, now, is that really the right answer? So I'm going to plug it back in. Try another one here. So that means that wherever I see an x, I'm going to put a negative 3 in its place. Negative 3 plus 4 is a 1. Same thing over here. 3 over 1 is 3. 3 minus 7 is a negative 4. And sure enough, negative 4 is the same thing as negative 4. The solution that I had come up with, in fact, was right. And that is how you solve your linear equations, well, rational equations, that is, not linear, but your rational equations where your denominators are a little bit more complicated. But there's not anything super difficult that you have to do with the denominators to find the LCD. Sometimes you have to do a little bit extra steps to get that LCD, and that's going to be in the next video.